Hello everyone! In today's video, we are showcasing the AI-ready PV demo project for N3uron MCP Server. This project is a pre-configured N3uron backup that provides a complete simulated PV plant environment for testing agentic AI workflows. The goal is to let users explore how an AI agent can interact with an industrial system through the MCP server without needing access to a real plant. Once restored, the project includes a structured data model, templates, real-time simulation, historical data, alarms, a Web Vision HMI, custom MCP tools, prompts, resources, and scripting logic. Although the demo is based on a PV plant, the same approach can be applied to other industrial environments where operational data, alarms, historical records, and technical context are important. For example, battery energy storage system, wind farms, water networks, manufacturing lines, substations, utilities, or remote industrial assets. The main value of the project is to understand the architecture behind industrial AI workflows. The data model, the context, the permissions, the tools, the SCADA integration, and the boundaries between the AI agent and the industrial system. Instead of starting from a presentation or a blank configuration, we start from a working project. Then we can restore it, inspect it, reverse engineer it, modify it, and adapt the same architecture to other use cases. The first place to start is the N3uron knowledge base. Here in the AI Ready PV demo introduction page, we can see the purpose of the project and the main components included in the backup. The documentation explains that the demo provides a complete environment for the MCP server module, including the simulated plant, the data model, the historian configuration, alarms, custom tools, prompts, resources, and the Web Vision HMI. It also explains the plant structure used in the demo. The project simulates a 10-megawatt photovoltaic plant with 10 power stations, 2 inverters for each power station, and a shared weather station. This gives us enough operational context to test realistic AI workflows, such as plant status summaries, performance analysis, alarm investigation, maintenance recommendations, and configuration audits. Before restoring the project, we need to make sure N3uron is installed on the node where we are going to run the demo. N3uron is lightweight, and this project is self-contained, so we do not need to connect to any external plant, PLC, database, or cloud service to start testing it. From the N3uron download page, we can install it on Windows or Linux operating systems. We also have deployment options for Docker, Kubernetes, AWS, Barbara, and Balena. The minimum system requirements for a basic N3uron installation are very low. A single core processor, 1 GB of RAM, and 1 GB of free disk space. However, those requirements are only for a minimal installation. As soon as we start adding more tags, modules, historical data, visualizations, or integrations, the node will need more resources. This demo project requires around 2.5 GB of RAM to run, but I recommend using at least 4 GB of RAM for this project if we also want to add extra modules later, such as MQTT client, REST API server, OPC UA server, or OPC UA client. For more information about hardware requirements, visit the N3uron hardware sizing guide in our knowledge base. In my case, I will install N3uron on my local Windows computer. The easiest way is to open PowerShell and use the wing it installation command shown on screen. This installs N3uron directly from the Windows Package Manager without having to download and run the installer manually. At the time of recording this video, the latest available version is N3uron 1.22.3. I recommend installing the latest version to benefit from the newest features, improvements, and MCP server capabilities. The installation is very fast and straightforward. Once N3uron is installed, the platform already includes all available modules for data acquisition, data delivery, edge computing, and visualization. We do not need to install each module separately. We simply create or instantiate the modules we need for each specific use case. After the installation, we open any standard web browser and access the N3uron Web UI to continue with the configuration. No external desktop application is required. The first time we access a new N3uron node, we are prompted to enter the administrator user credentials. In this example, the administrator user is named admin. Once N3uron is installed and we have access to the web UI, we can go back to the knowledge base and continue with the next step, downloading and restoring the AI-ready PV demo project backup. Now we continue from the AI-ready PV demo initial setup page in the knowledge base. This page explains the basic steps required to get the project running in our N3uron node. First, we need to download the AI-ready PV demo backup. To do that, we open the download form, fill in the required information, and submit it. After submitting the form, you will receive an email with a link to download the project backup. The backup is delivered as a zip file, ready to be imported into N3uron. Once the file has been downloaded, we go back to the N3uron Web UI. From the left navigation panel, we go to System, then Config, and then this node. Here, we open the Backup Manager. Inside the Backup Manager, we click Import and select the zip file we downloaded. After the backup has been imported, it appears in the backup list. To restore the project, we open the three-dot menu for that backup and select Load. N3uron asks for confirmation before loading the backup and restarting the required modules. We click OK to continue. At this point, N3uron restores the complete AI-ready PV demo project in the node. This includes the main modules used by the demo: Web UI, derived tags, Historian, MCP Server, scripting, and Web Vision. After the restore process finishes, we need to log in again to the Web UI. For a fresh installation, the default administrator user is admin, and the default password is N3uron. For security reasons, it is recommended to change the default password after the first login. Once we are logged in again, the AI-ready PV demo project is restored and ready. Now that the project has been restored, let's take a quick look at the main modules included in the demo. In the Modules section, we can see the components that make the project work. Derived tags is used to calculate values from other tags. For example, active power averages, plant and station KPIs, and performance ratio calculations. Historian is used to store tag values, events, and alarms. In this demo, the project uses embedded MongoDB, so everything remains self-contained. The retention policy is set to 3 months, which is more than enough for testing and analysis purposes. Web UI is the graphical interface we are using right now to configure and manage the node. Web Vision is used to design and view the PV demo HMI. And finally, MCP Server and scripting are the modules that expose the project to the AI agent and execute the logic behind the custom MCP tools. We will review those in more detail later. Before going deeper into the configuration, let's open the Web Vision HMI. This gives us a better understanding of the simulated plant. Here, I am showcasing a plant overview including active power, daily energy, performance ratio, capacity factor, weather station values, inverter status, trends, and alarms. This Web Vision HMI is useful because it shows the project as an operational system, not just as a configuration example. Now let's go back to the Web UI and open the tag configuration. The tag model follows the structure described in the knowledge base. At the top level, we have the PV plant. Below that, we have power stations, inverters, plant KPIs, station KPIs, the weather station, location information, and alarm-related tags. The project also uses templates and subtemplates to keep the model consistent. This is very important for AI workflows. The agent needs a clear and predictable structure to understand the plant, identify assets, compare similar equipment, and call the right tools with the right paths. Metadata is also critical. Descriptions help explain what each tag represents. Data types define how values are handled. Engineering units tell the agent whether a value is in kilowatts, kilowatt hours, volts, amps, percent, or another unit. Scaling ensures that raw values are converted into the correct engineering values. And historization defines which tags are available for trend analysis and historical queries. Now, let's open data and go to historical. Here we can run one of the preset historical queries. Since we have just restored the project, we might see that there is not much historical data yet. Only the values generated since the project started are available. This is why the demo includes a backfill mechanism. The backfill creates historical data for the previous 90 days from the moment it is executed, so we can immediately test reports, trends, performance analysis, alarm investigation, and maintenance workflows. In my case, I have already run the backfill before, so there is already historical data available. But we are going to run it again to show the process. To do that, we go to the backfill tags. The main tag is request. When we write true to request, the backfill process starts. The running tag tells us whether the process is currently active. The progress percentage tag shows how much of the process has been completed. The status tag gives us the current execution state. And the last start and last end timestamps in UTC show when the last backfill execution started and finished. There is also a very important tag here, underperformance. This tag allows us to decide whether the backfill should generate normal historical data or include a controlled low-performance scenario. When underperformance is set to false, the backfill generates normal production behavior. When underperformance is set to true, the backfill injects a simulated underperformance condition into selected assets. This is essential for testing AI workflows. If all assets behave normally, the agent can only produce normal status summaries. But if we inject a controlled issue, we can verify whether the agent is able to detect the problem, identify the affected assets, compare them against the rest of the fleet, and explain the evidence using historical data. In other words, the underperformance tag gives us a safe way to create a realistic fault scenario without connecting to a real plant. Now let's move to the MCP server configuration. This is the part of the project that makes it AI ready. The MCP server is the module that allows an MCP client, such as Claude Desktop, to connect to the N3uron node and interact with the project in a controlled way. The connection is configured from the MCP server module instance. Here we define how the server will listen for MCP clients, using HTTP, HTTPS, or both. For local testing, HTTP can be enough. For more realistic or production-like environments, HTTPS is the recommended option. If we use HTTPS, we need a certificate. We can either create a new self-signed certificate from N3uron or import our own certificate. When using a self-signed certificate, the MCP client machine must trust it. In my case, I have already created the certificate, so I will download it to my local machine and install it in the Windows Trusted Certificate Store. This step is important because if the client does not trust the certificate, the HTTPS connection will fail. After the connection settings, we review the access configuration. The MCP server uses bearer tokens to control what each client can access. After restoring the backup, it is important to create a new bearer token. The token value is displayed only once, so make sure to copy it and store it in a safe location before closing the window. We will need this token later when configuring the MCP client connection. If the token is lost, we should generate a new one and update the client configuration. This is one of the most important parts of the architecture. With the token, we can decide which built-in tools are available, whether custom tools are allowed, whether custom prompts are available, whether resources can be accessed, and which tag paths are visible to the client. This means the AI agent only sees the capabilities and context that we explicitly expose. For a demo, we can enable enough permissions to explore the project. For a real deployment, we should keep the access as limited as possible and only expose what the specific workflow requires. Now, let's look at the tools. The MCP server includes more than 40 built-in tools. These are generic platform tools that allow the client to work with standard N3uron capabilities, such as tags, alarms, logs, modules, backups, certificates, licenses, system status, links, and redundancy. Built-in tools are useful because they give the agent a standard way to inspect the node, browse the tag model, read historical data, check alarms, review module status, or audit the configuration. But this project also includes custom tools. Custom tools are different because they are specific to this PV demo use case. For example, a custom tool can summarize the daily plant status, scan the fleet for underperforming assets, analyze alarm patterns, compare yield, recommend maintenance actions, or audit the node configuration. The key point is that custom tools allow us to keep deterministic calculations, business rules, validation logic, and guardrails inside N3uron. For example, a custom tool can define exactly which tags are read, which formulas are used, which thresholds apply, what data is returned, and what information should remain hidden. This helps with reliability, privacy, and control. The AI agent calls the tool, receives structured evidence, and then explains the result to the user. When we open one of the custom tools, we can see its name, title, description, input schema, output schema, and the scripting script it is linked to. The input schema defines what arguments the agent can send. The output schema defines the structure of the result returned by the tool. To link the tool with the logic, we select the scripting instance and the corresponding script name. That script must exist in the scripting module and must be configured so it can be invoked externally by the MCP server. Now, let's look at custom prompts. Custom prompts are reusable instructions for common workflows. For example, checking the plant status, finding the worst performing assets, investigating a problem, creating a maintenance plan, or auditing the configuration. Prompts are useful because they give the user a guided way to start an analysis without writing the full instruction from scratch. Next, we have resources. Resources are documents or text content exposed to the AI agent through the MCP server. In this project, the embedded resource is the Xantrex G500 inverter documentation. This is the inverter model used as technical reference for the demo, and the document has been converted to text so MCP clients can read it more reliably. This resource allows the agent to combine operational data from the node with equipment-specific documentation. For example, if the tools detect an inverter performance issue, the agent can use the operational evidence together with the Xantrex GT500 documentation to produce a more useful and specific recommendation. This is another part of context engineering. The agent should not answer only from generic knowledge. It should answer from the actual node context, the tool results, and the technical resources that were intentionally exposed. Finally, let's open the scripting module. Here we can see the scripts used by the MCP server custom tools. Each custom tool calls a script. The script receives the tool arguments, executes the logic, and returns a structured JSON response. In this project, the scripts are intentionally thin. Most of the reusable logic is placed in a shared library. This makes the solution easier to maintain because calculations, validation, data access, and response formatting can be reused across multiple tools. So the pattern is clear. The MCP server exposes the tool. The token controls access. The input schema controls what the agent can send. The scripting script executes the logic. The shared library contains the reusable functions. And the output schema controls what the agent receives. For more details about MCP server configuration, custom tools, prompts, resources, and scripting integration, the knowledge base includes dedicated pages for each part of the project. One useful tip is that if the token has read access to the module configuration, the AI agent can inspect the project and explain how it is built. It can even generate a report describing the data model, the modules, the tools, the prompts, the resources, and the scripts. And from there, it can also suggest improvements, new tools, or new scripts that we can adapt to our own use cases. This is why the project is useful as a learning reference. We can restore it, inspect it, ask the agent to explain it, and then use the same architecture to build our own industrial AI workflows. Now it is time to test the MCP server from an AI agent with MCP capabilities. In this example, we are going to use Claude Desktop. Before configuring the client, it is useful to know that the N3uron knowledge base includes configuration examples for different MCP clients and AI tools. Here we can see the Claude Desktop configuration example using the Claude Desktop config JSON file. For this video, we are going to connect Claude Desktop to the N3uron MCP server using HTTPS. In my case, the MCP server is running locally, so the endpoint points to localhost, using the HTTPS port configured in the MCP server module. Because we are using HTTPS with a self-signed certificate, the certificate must already be installed in the trusted certificate store of the machine where Claude Desktop is running. We already did that in the previous step. Now we open the Claude Desktop configuration file. In Windows, this file is located under the Claude folder in the User App Data Roaming directory. Inside the configuration file, we add a new MCP server entry. In this case, the server is called N3local. The command uses npx and MCP remote to connect Claude Desktop to the N3uron MCP endpoint. The URL points to the MCP server endpoint. The authorization header uses the bearer token we generated and saved earlier. And because we are using a trusted HTTPS certificate, we also enable the System Certificate Authority option. After saving the configuration file, it is important to restart Claude Desktop. Claude Desktop only loads the MCP configuration when the application starts, so if we do not restart it, the new MCP server may not appear. Once Claude Desktop is restarted, we open a new chat. If we click the plus button in the prompt area, we can see that our N3uron MCP server is now connected and enabled. From here, Claude can access the capabilities exposed by the N3uron MCP server, depending on the permissions configured in the bearer token. We can inspect the available prompts, such as audit configuration, check plant status, explain recent downtime, find worst assets, investigate problem, and make maintenance plan. We can also see resources exposed by the server. For example, the module log files are available as resources. This is very useful because the AI agent can use the logs to help diagnose configuration issues, module errors, or troubleshooting scenarios. We can also see the Xantrex GT500 datasheet, which is the inverter documentation embedded in the project. This allows Claude to cross-reference operational findings with the technical documentation used in the demo. Now, let's create a more complete test. We will start from the Find Worst Assets prompt, which is one of the custom prompts exposed by the MCP server. Then we will also attach the Xantrex GT500 datasheet as a resource, so the agent can use it as technical context. In addition to the predefined prompt, we are going to add free text to request a more complete analysis. For example, we can ask Claude to find the worst performing assets, run a full system audit, analyze alarm patterns for the last 45 days, create a maintenance plan, and generate all the results as a comprehensive interactive HTML report ready to download. This is a good test because it combines several MCP capabilities at the same time. Claude can use the custom prompt to guide the workflow. It can call the custom tools to perform deterministic analysis. It can use built-in tools if it needs to inspect tags, alarms, module configuration, or historical data. It can read the Xantrex GT500 datasheet for equipment-specific context. And the important point is that the answer should not be based on generic assumptions. It should be grounded in the data, tools, prompts, resources, and permissions exposed by the N3uron MCP server. This is where the AI Ready PV demo becomes really useful. We are not only chatting with an AI model, we are giving the agent controlled access to an industrial project with a structured data model, historical records, alarms, technical resources, and custom analytical tools. Now we can run the query and review the report generated by Claude. Here we can see the HTML report generated by Claude using the tools and resources exposed by the N3uron MCP server. This is not just a generic text response. The agent has used multiple MCP tool calls to collect evidence from the node, analyze plant performance, review alarms, inspect configuration quality, check system status, and generate a structured operations and maintenance diagnostic report. The report is for Blue Lake, General PV Plant Site 1, and the overall status is critical. The first area to review is the executive summary. Here, the report immediately highlights two main issues: chronic underperformance in 2 inverters and a high alarm volume across the plant. The underperforming assets are Power Station 3, Inverter 1, and Power Station 6, Inverter 2. Both are around 28% below the fleet mean over the 45-day analysis window. Their health scores are also very low, close to 16 out of 100. What makes this more useful is the comparison against the paired inverters in the same power stations. The paired inverters are healthy, so the issue does not look plant-wide. It looks isolated to 2 specific inverter units. The report also estimates the business impact. Each affected inverter produced roughly 33,000 kilowatt-hours less than its healthy peer during the analysis window. At fleet level, this represents an estimated energy loss of approximately 66 megawatt-hours. This gives the maintenance team a clear priority. Start with those 2 inverters. Now, let's move to the alarm situation. The executive summary reports 3,381 alarm events from 6 recurring alarm paths with 0 acknowledgements. This is why the report classifies the alarm subsystem as being in a chronic flood state. If we go into the alarm details, we can see that the top recurring alarms are the status alarm, power low alarm, fault alarm, and communication alarm. Each of these alarms triggered hundreds of times during the 45-day window. The fault alarm is especially important because it is a critical alarm and its mean duration is close to 29 minutes per event. That pattern suggests repeated fault and restart cycles, rather than a single short transient condition. The report also shows major alarm burst clusters. Some of these clusters lasted many hours, and the largest ones include more than 200 events. This is useful because it helps the operator understand not only which alarms occurred, but also when they were concentrated and how long the alarm burst lasted. Next, let's review the configuration audit. The report confirms that all 6 modules are running and that there are 0 system errors. It also shows that the audited critical tags pass the main quality checks. The tags have descriptions, engineering units, historical configuration, and good quality values. That is important because reliable AI-assisted analysis depends heavily on a clean tag model and good metadata. At the same time, the report highlights several operational warnings. The last backup is more than 10 days old, while the threshold used in the report is 48 hours. Disk usage is also high, at around 85%, and several modules are running in demo license mode, which is fine for this test project, but not suitable for a production deployment. When the report shows RAM usage, we can also see that it is relatively high. In this case, that is expected because I am running the demo on my local computer, and I also have many other applications running at the same time. So this RAM value should not be interpreted as the normal memory footprint of the demo project alone. Finally, let's look at the maintenance recommendations. The report prioritizes a field inspection of Power Station 3, Inverter 1, and Power Station 6, Inverter 2. It recommends checking inverter fault information, DC input conditions, combiner fuses, communication wiring, and relevant inverter settings. It also recommends acknowledging the pending alarms, reviewing the alarm workflow, and creating a new N3uron backup. This is the key point of the demo. The agent is not just producing a high-level summary, it is combining historical data, alarm patterns, system configuration, module status, custom tool results, and the inverter technical documentation. The result is a practical report that explains what is happening, why it matters, what evidence supports the findings, and what actions should be taken next. This is exactly the type of workflow we want to test with the AI-ready PV demo project. And with this report, we have completed the full workflow. We started from a restored project, exposed it through the MCP server, connected Claude Desktop, and used the available tools and resources to generate an operational analysis. From here, the next step is to adapt the same pattern to your own environment. Replace the model, adjust the tools, update the prompts, add your own resources, and define the right access permissions. You can also complement the AI agent with agent skills to provide additional N3uron knowledge, procedures, and best practices alongside the live MCP context. Thanks for watching.